Hello everybody, welcome back to General Science, and today we're going to talk about the periodic table and periodic trends. In the last episode we talked about the history of atomic structure and how that's changed over time, and now the best kind of way to explain what all that kind of meant is to go to this document here, which is the periodic table of elements. This is the latest, greatest, and updated one. It has all the elements on it, even the latest ones on it. As you can see my mouse down here, these are all the newest ones. Okay, and this has got a lot of information on it. So if you know how to read this table, you can know a lot about chemistry, and you can use it as a tool to do a lot of chemistry work. So we're going to talk a little bit about it and what it all means. Okay, so the first things first, each one of these squares on the periodic table is an element. Okay, so this is the smallest possible group or smallest possible thing of something, so that makes it an element. And right now we have 118 of them, so there's 118 elements. Okay, and scientists are pretty sure this is going to be the amount that we have for a while now. No new ones coming anytime soon, and that's because each element is unique because it has a certain amount of protons. Those are those positively charged particles we talked about in the last video. The number of protons is what determines what element it is. Okay, so if you go through the periodic table, right, hydrogen over here is number 1 because it has 1 proton in it. Helium has 2 because it has 2 protons, and so on. So if you go all the way through this list, each one of these elements has more and more protons in it, and that is why they are an element, because they have a certain distinct number of protons. Okay. Now, what about those other subatomic particles we talked about? We talked about neutrons, and we talked about electrons. So the electrons, they are going to always be the same as the number of protons, because atoms or elements also need to be balanced. They have to have a neutral charge. And so that means if hydrogen here has 1 positively charged proton in it, there has to be 1 electron in there to balance it out. So one standard hydrogen atom is going to have 1 proton and 1 electron. Same goes for any of these here. So if you go through and you pick one, let's say number 25, manganese, right? It has 25 protons. That means manganese is going to have 25 electrons in it in its standard configuration. Okay. Now for the neutrons, we can figure that out looking at this table as well. As you can see, in each one of these, there is a number at the bottom there. Okay, and that number is the atomic mass. So how much does the average atom of this thing weigh? Okay, and as you can see, it's different from the atomic number, which is how many protons it has. So we found out through a lot of study that protons and neutrons weigh roughly about the same amount. They're a little bit different, but for the most part, they're the same. And because they're so small, we gave them a special unit. It's called an atomic mass unit. And so a proton is 1 atomic mass unit, and a neutron is 1 atomic mass unit. So if you take a look here, let's look at manganese one more time. It says that the average manganese is 54.9 atomic mass units. And since there's 25 protons, if we did some math here, that means there's roughly 29 neutrons in a manganese atom. Because remember, electrons don't weigh that much. They're super, super tiny. They're like 0.001 right, atomic mass units, so they don't actually add up that much in the total weight of these atoms. Okay, so there's some pretty interesting information right there as to what you can see. Okay, now let's talk about the structure of this table. As you can see, there are huge gaps in between, okay, these different elements. Okay, and then actually this huge row down here, the yellow or the orange and red one, is actually supposed to be right here. Right here. Okay, now the reason that's the way it is because of the way the electrons are sorted into the atoms in the periodic table. Okay, we talked a little bit about this in the last video, but electrons go into what these things called orbitals, and orbitals have limits as to how many electrons they're able to carry. Okay, so the most basic orbital, the smallest one, the very first orbital that an electron can be in, can only hold 2 electrons. And so that's why this first row here only has 2 elements in it. It's because those 2 elements, right? This one has 1 electron and this one has 2. And so now once you've filled those 2, the next element up has 3, so it's going to be up a row of orbitals, okay, and so on and so forth as you go down through this table. Okay, so the periodic table is shaped based off of these electron orbitals. So really, the electrons and their position within the elements is really important. That's why we've based the table this way, but it's also because electrons and their position in elements play a major role in the actual properties of these elements. So all these elements have certain properties, these certain things that they're able to do, certain things that they're able to react with, and that's all because of how many electrons they have. Okay, so, right, hydrogen is a pretty reactive element. It's going to react pretty rapidly, and that's because it's only got 1 electron in it, right? And all of the things in this row are very reactive because of that. These guys over here, they have full orbitals. Their orbitals are filled up. They are not reactive. They don't really react that much because they have all the electrons they need. Their orbitals are full. There's no need to get more. Okay, so like I said, right, the electrons have an important role to play in the structure of this table. Now let's take a look at some of the different colors and things on here and why they're important. Okay, we've sorted several of these different things into kind of categories. Okay, so for instance, these are the alkali metals, these are the alkaline metals. These are called transition metals. Notice that they're all in this section of the periodic table. These are the noble gases. They're called noble because they don't react. These guys here are nonmetals, and these are elements that are generally gases when they're out and about being elements. And then down here, right, we've got other metals, and these guys are the lanthanoids and the actinoids. They have special rules because they have this extra type of orbital that they can have. So they're colored that way. But then there's these other kind of colors that we have in here. Okay, as you can see up here, we've got solids, liquids, and gases, and then also this synthetic one. Okay, now solids, right? These things you can actually find hunks of metal of these elements, right? You could go and dig in the ground in the right spot, and you could pull out a piece of cobalt, a metal piece of cobalt, or you could go dig in the ground and find copper, right? Those things are solids when they're out and about in nature. Okay? Liquids are things that you'd find as a liquid in nature, like mercury, right? Mercury is usually a liquid. It's that silvery liquid that if you've ever held in your hand, it feels really weird. Not really supposed to do that because it's toxic, but you know what I mean, right? You could find it in this liquid form. And then all these guys are gases, the red ones, like helium. Helium is a gas, right? You put it in balloons, it makes your balloons float. You can breathe it in and it makes your voice really high, right? You're going to find those things as gases. Same thing with like oxygen, right, which is in the atmosphere, or nitrogen, which is also in the atmosphere, right? All these different things are generally gases in their natural state. Now, this one says synthetic, and a lot of people ask, okay, what does that mean? What is a synthetic element? Okay, basically, these are elements that don't exist naturally in the universe, right? You can't go around and find technetium somewhere, right, without going to a lab and making it, having scientists make it for you. These elements are special because they were made by human beings, right? Basically, what happened is through an experiment, we rammed enough protons together to end up getting 43 in this element, right? And so these elements are entirely man-made, and a lot of them haven't actually really been around that much. And they're also usually have really funny names. So, for instance, like the first one was called technetium. They've got promethium, right after Prometheus. Neptunium. So a lot of them were named after like Roman planets. This one was called americium because it was discovered in America. You got curium because it was named after Marie Curie. Berkelium, was discovered in Berkeley, California. Californium, where does that one get made from, right? Like all these different ones, they're named after scientists and places. And so these ones are man-made, so they've been named after scientists who helped discover the atom, right? You can see you got Mendelevium, right? He was the one who made this table. You got Rutherfordium. He helped make atoms, like discover the things about the atom. Bohrium, Bohr helped do that too. And then you've got other different people like Copernicus. And then once you get down to here, you start getting more countries and states and stuff like that, right? Like Nihonium, that one was discovered in Japan, I believe. Moscovium was discovered in Russia. Tennessine was discovered in Tennessee. And then Ognesium, I think, is after a natural scientist. Right, all these different elements, though, were created by man, so they're synthetic. And so you'll notice that a lot of them, instead of having these like decimal numbers as their atomic weights, they're going to have these really like rough estimate numbers, like they're just 268. Right? That's because a lot of these elements only existed long enough to get like a rough idea of how many neutrons and protons they had. And so we know how many they had in that like couple seconds they existed, but they've only existed that one or two times. So we don't have enough of a data pool like we do for all these other elements to get a more refined number. Like for instance, niobium, right? There's enough of it that we've been able to narrow it down to exactly this is this weighted average. Whereas these ones, right, it's more set. They have a very limited data set when it comes to their atomic weight. Some of them, right, they didn't even exist long enough for us to know what their atomic weight was going to be. So Nihonium, Moscovium, Tennessine, Ognesium, we don't know what their atomic weight is. We're not 100% sure. They only existed for like a second or two. And so we didn't get enough data to really understand their structure the way that we've had these other elements. So now the last thing I wanted to talk about when it comes to the periodic table is we've noticed, right, that these orbitals are what's organizing all of this. And that means that certain elements are bigger than others, and that's because of their position on the table. Right? Turns out, the further to the left you are on the table, the bigger an element is. Okay, the electrons are more spread out, and so they end up taking up a little bit more space. And as you move to the right, they end up getting smaller and smaller and smaller. Same thing goes when you're going down. They're smaller up here because there's less electrons, and as you go down and down and down, the more orbitals add up, and there's more electrons packed further out and further out. So as you go to the left and down, you're going to get bigger and bigger and bigger elements, and you're also going to get smaller elements as you go up and to the right. The other thing that you need to know about for the periodic table is what things are going to be the most reactive. And now, honestly, this last row here is the least reactive because they're the noble gases. They don't really react that often. But the things that are closest to the noble gases, so this line right here, okay, known as the, I forgot their name. They have a special name, but this row here and then this row here are going to be the most reactive. Basically, the closer you are to this noble gas row, the more reactive you're going to be in general. It doesn't always work out that way, but generally that's how it works. The more reactive you are, the closer you are to this noble gas line. Okay, and that's because atoms, in essence, what they want to do is fill those orbitals up. It kind of feels uncomfortable to have your orbitals not filled. And so that's kind of how we describe it. And that's not actually true, right? Atoms don't have feelings. At least we don't think they do, right? Maybe they do. We're not sure. We haven't actually talked to an atom yet, right? But right. So fluorine here, right, is missing one electron to have a full set of orbitals like neon does. And so fluorine is going to react with anything that can give it an electron and make it feel like neon, right? Same thing going here with lithium. Lithium has one extra electron than helium. And so lithium, right, is going to be willing to give up that electron to anybody who will take it so that it can feel like helium. Okay, that's how chemical reactions work. It's all about the exchanging of electrons, and that means that if you can look at the periodic table and realize where they are and how many electrons they have compared to this nice noble gas line here, you're going to see just how reactive those elements are because of that. Anyway, thank you so much for watching this video about the periodic table and everything it can teach us. I hope you're enjoying the series. And next time we'll talk more about what these reactions elements can do, and the properties of the things that they make. Thanks so much for watching. Enjoy your day.